Welcome to qnawire.
For A, the question is asking us to determine the period of vibration, which is T. And based on the equation, T equals to 1 over F. And since we know the frequency F, we can just plug it into the equation. So it becomes 1 over 6.0 hertz. And that will give us an answer of 0.167 seconds. For B, we have some different variables now. So it's asking us to determine a new frequency. Let's name it F1. And we have the mass of the cart and also the spring constant. Let's call it K. So first, we need to figure out what kind of equation we can use that includes all three of the variables. And the answer would be F equals to 1 over 2 pi with K over M under the square root. This is the equation that we can use since it has all three of the variables, F, K, and M. And now, we don't know K and we don't know M, but we know that it has changed after from the original value. So let's write a system of equation. The first one would be, let's name it equation 1, which is the equation for the original frequency. 6.0 hertz equals to 1 over 2 pi square root of the original spring constant and the original mass m. And now we have a new frequency that we are asked to figure out. And we say that it's f1 and 1 over 2 pi. Now we know that the spring constant is the same, but we have a mass that's twice before, so we will say it's 2 times m, because m is the original mass of the cart. So how do we solve this f1? Well, the way to think about it is to see how equation 2 differs from equation 1. So if we can take the 2 out, we should be able to figure it out. So let's do a little bit of alteration of equation 2. So 1 over 2 pi equals to actually square root of 1/2 times square root of k over m. And then we can do it further by putting square root of 1/2, which is 1 over square root of 2, at the front of the equation, and it's going to be looking like this. The later half, the second half of the equation looks rather familiar because you can easily tell that it's exactly what we have in equation 1, which means the equation 2 eventually leads us to have 1 over square root of 2 times 6.0 hertz. And we know that this is how we're going to solve f1. So if you just simply use a calculator to do the calculation here, it's going to lead us to the answer of 4.24 hertz. And for C, the thinking process is rather similar. For now, we're still going to be using the same equation, but instead we know that the spring constant doubles now while the mass remains the same. So we still have the same equation 1 over there. And now I'm gonna write equation 1 real quick, just for reference. So 6.0 hertz equals to 1 over 2 pi times square root of k over m. And now we have equation 2, a new equation 2, with f2 equals to 1/2 pi, but instead we have 2k because the spring constant doubles and we have the same n. Now we do the same, which is taking the 2 in front of the k out of the square root. So in that sense, we have 1/2 pi times square root of 2 and square root of k over m. So in the end, it's going to be square root of 2 times 1/2 pi k over m square root. And it's exactly the same as what happened in problem part B of the problem. So in the end, we will have square root of 2 times 6.0 hertz, and they'll give us the answer of 8.49 hertz.